So now I'm going to evaluate the strengths and weaknesses of numerical models and the use of the method of the force plates. So the first advantage includes some of the consistent controls in place. Each person in the group was told the same information as the instructor announced the information to the group rather than to each individual. And this meant that everyone heard exactly the same idea and they had the exact same idea of what to do. As if telling each individual person, it could mean that people ask questions or are told different things. So by telling everyone, the method was relatively standardized from one person to the next. And this means that there's increased replication. And if it was to be repeated, it would be more likely to find similar results. And this would therefore increase the reliability of it due to the standardized aspect of it. And then another advantage is that the data provided can be used to track change. The data is numerical, meaning it can be analysed, used to draw conclusions, and graphs can be made which show the data visually. This information can then be used to determine what needs to be improved on in terms of a person's technique, or what area a person may be weaker on. For example, results may show that a person doesn't generate much velocity in their jump, and velocity is one of the most important factors in a high jump. Therefore, knowing this information means that the area of weakness can be worked on. So improving the height of a jump in a box out and rebound. So knowing this will be able to help them in a game situation. Also, progress can be tracked to see if these improvements are working effectively or not. It can be used by biomechanics to tell them how to optimize the performer's technique, and whether maybe one aspect of a person's performance or jump is weaker than other and needs to be worked on. So it highlights weaknesses in technique, which can then inform improvements that need to be made. And if the force plates are used properly, they can be very accurate. However, there are many weaknesses of numerical models. The first disadvantage of the method was that it was prone to human error and is therefore subjective. First of all, when measuring the angle of a joint, a person was doing this by eye, and so it's likely that it's not exactly 90 degrees or 135 when measuring it. And when the person actually did the jump with a specific angle, it's highly unlikely with this method that they had the bend of the exact correct angle. This would have impacted their results, as some people may have had a greater angle on their bend, meaning that they would have been able to get a higher jump and generate more power. This is because a greater angle of bend allows more energy to be stored in the muscles, which can then be transferred upwards. Newton's third law of motion, action and reaction. The next part of the method, which is subjective, includes when using the software, picking the phases, starts and ends. A person has to judge by eye where the phase starts and ends and position the line accordingly. Judging by eye is highly subjective, as it's likely a person may make a mistake or misjudge where the phase began, or different people would interpret it differently, and this would impact the results gained. For each person's jump, this would have been done, which highlighted how time-consuming and fiddly the method is. Each person altogether did 6 jumps, and so looking at each jump, picking the start and end phase took an extremely long time, and this is a major disadvantage of the method. A software that was more advanced and did this for you, so positioned the line for you and told you the results, would be much better, but mean much more expensive likely. The way of standardizing the angle better would be by if you had a cone or a kind of something that your leg would hit as soon as you hit the exact angle, and then you'd know exactly when to jump rather than guessing when you'd hit an angle. Another disadvantage was that the technique required for the jump wasn't very clearly specified. Some people were using their arms, some weren't, some took a wider stance, etc. All these differences would have impacted on the results, and therefore the height the person could jump. To improve this, the technique should have been more clearly specified and more standardised, as this could have a major impact on the results gained. Also, the technique for jumping was not very natural, especially on the 90-degree angle. Participants should have had the opportunity to familiarise themselves with the jump before, as it tends to be that people's first jumps are the worst, as they're getting a feel for what they're required to do and adjusting to the potentially unnatural kind of feeling. Ecological validity is very low and is very affected as it's not done in a natural setting, which in this case would have been on a basketball court in a game of training. It's conducted in a lab where someone is in a completely unnatural environment. The jump that was required of each person did not feel much like a jump in a basketball court or in a box out and rebound. The jump, first of all, was static and was on the spot, whereas in a game situation, a person wouldn't be so static and there would be motion before taking off in their jump. So therefore, what was required was unrealistic for a box out and rebound. Now going to be looking at graphs. So this graph is showing the resultant force, which is calculated via minusing body weight from mean force. So I've compared the stronger player and the weaker performer for each of the different aspects, and I've got a group mean as well. So this one's the resultant force. So the stronger person had a much greater resultant force than the weaker person. They had 680 newtons in comparison to 79 newtons. This therefore tells us that a greater force was generated by the stronger performer in comparison to their body rate. If a greater force was generated, they were able to jump higher into the air. The stronger performer had a greater resultant force, and therefore the forces were more unbalanced for him, as the force powering him up was greater than the gravity acting upon him. The graph here is showing the duration of the phase in seconds. The weaker performer had a greater duration of phase of 0.504 seconds, whilst the stronger performer had a shorter duration of phase of 0.405 seconds. And the weaker performer was actually above the group mean, whilst the stronger performer was actually below the group mean. And then this graph here shows the net impulse. So the net impulse for the stronger performer was 275, whilst in newtons per second, whilst for the weaker performer was 141. The graph therefore tells us that the stronger performer had a greater amount of force being generated and over a greater period, allowing them to have a greater impulse. As an impulse is equal to the net force of an object times the time period at which the force is applied. So the stronger performer had a much greater force than the weaker performer, which would have an impact on their height that they jumped, which I'll talk about later. So this graph here is showing the mean velocity in meters per second. It's calculated by dividing impulse by mass. The velocity of the weaker performer was 2.3, whilst for the stronger performer was 3.4 meters per second. As velocity is one of the most important factors when getting a high jump. The reason why the performer had a greater height, which I'll talk about later, was because they generated a greater velocity. This greater velocity generated was able to power the stronger performer higher into the air, therefore having an effect on the height of the jump. This is also to do with the stretch-shorten cycle. So, as a person is going in the downward phase, this is the eccentric phase, this is when energy is generated. Then, quickly going into the concentric phase, which is the upwards phase, means that all the stored energy is then released, translating into a higher jump for an individual. Potential energy is stored during the eccentric contraction and downward phase, and then rapid transition leads to greater power upwards, and then larger force produced during concentric contraction of the upward phase, so greater velocity is much better. The next graph is the acceleration, and this graph is showing the acceleration in meters per second, which is calculated via force divided by mass. The weaker person didn't get anywhere near as much acceleration on their jump, with a score of 4.58 meters per second, whilst the stronger performer had a much greater amount of acceleration, enabling them to jump higher. This final graph here on the page is showing mean power measured in watts. The power which is generated is so important in an effective jump. The more power that is generated, the more power generated, the better, as it shows that the action and reaction between the person and the force plates was much larger, therefore propelling the stronger person into the air, as they had more power, and so there was more explosion from the force plates, and the stronger person got a much greater mean power of 2,229 newtons in comparison to the weaker performer who only got 644 newtons. This shows the importance of generating power in achieving a high jump. So the stronger player got a much stronger power than the weaker person. And all of these different graphs that I've just shown you all basically add up to and contribute to the most important aspect, which is the time in air and the jump height. So the time in air essentially is how high the person jumps, and it tends to be that with a greater power, acceleration and velocity, etc., a person can jump higher, and if they've jumped higher, they will therefore spend a lot longer time in the air. As shown by the graph, the stronger performer had a longer time in air of 0.63 seconds, whilst the weaker performer only had a time in air of 0.4 seconds, which is low compared to the stronger performer and also to the group mean, therefore showing the importance of these other factors in contributing to the time in air, as the stronger player had a much higher air time. And finally, this graph is the jump height calculated in meters, which is super important. So the jump height, so the weaker jumper got a score of 0.2, whilst the stronger performer obtained a jump height of 0.49. This therefore shows that all the different factors add up and contribute to the height of the jump. So therefore, a person who has greater acceleration, velocity, power, impulse, etc., will therefore get a higher jump in, for example, a box out and rebound. And if they're able to jump higher, they will therefore be able to retrieve the ball. They'll be more able to retrieve the ball and more likely to win the ball because they're able to jump higher, meaning they're able to grab the ball, make contact with the ball before someone who gets a lower height. So it's very advantageous to have a higher jump height. So the stronger one got one 0.49, whilst the weaker only 0.2. So comparing the two, is the difference between the scores is 0.29 centimeters. And then compared to the group mean, the performer had a greater score of 0.3 more. All the different aspects involved just contribute to the jump height, which is why the stronger performer on all these different factors scored better, meaning and adding up to them having a greater jump height and a greater time in the air, as the weaker performer didn't do so well on acceleration, mean power, etc., meaning that they didn't jump as high, and also meaning they had a less time in air in seconds. And finally, here is some photos of us on the force plates and with the gynometer in my hand there, and this is evidence of the practical when we went to the lab.